Good afternoon.
Hello, everyone. Nice to see you. How are you doing?
Hello.
Hello.
Hi.
How are you?
Good afternoon.
Hello.
Good, thanks. How are you?
I'm normal.
Good afternoon.
Good afternoon. Hope today we will not have any internet issues. So we introduced last time concept of electrostatic potential, and today we continue this discussion. In particular, we will focus on electrostatic potential next to a point charge. So we will take into account this symmetry of electric field created around point charge. We'll calculate how electrostatic potential is changing versus distance from this point charge to any point in space. And also, we will also practice with going backwards, determining electric field if known potential distribution. That has certain advantages. We will mention about them. So it's kind of, if we have a system of electric charges, it is easier to calculate resultant electrostatic potential and then determine electric field from that distribution of electrostatic potential. In the contrary, it could be difficult to do, and during this discussion, we will explain why. So let me switch to our slides. And as I said, we will consider some point charge. Will be Q, let's say positive charge, or it doesn't matter. Then we have 2 points, point A, point B. There is initial position vector R, which defines position of like this point A with respect to the electric charge. Here is this position vector in the final position. And there was some path. Let's say, maybe let's make it dashed. Something like this. So we can pick up some point on this path from point A to point B. Draw this intermediate like position vector. Also tangential, larger angle we need. Tangential to this path will be displacement vector ds. Then at this point, we describe the system as we wanted. In addition to this, we need to add unit vector R, which will define the orientation. So it will be from the point charge Q in radial direction. So now if we want to determine potential difference between points B and A, so we can write VB minus VA. That will be equal to minus integral from point A to point B of dot product electric field vector and displacement vector. So that is from our previous discussion. We know how we can calculate in general case potential difference. At the same time, we also know how electric field vector can be expressed. I mean electric field created by a point charge. So we can write E vector is equal to KE, constant, times Q, electric charge, divided by R square, distance from electric charge to that point where we want to determine electric field vector, and times this R unit vector, which defines the orientation. So now let us focus on this argument of the integral, like body of the integral, how it will look in our particular case when we deal with a point charge. So E vector dot product with ds vector will be equal. So instead of E vector, we substitute its expression. So it will be KEQ divided by R square times R unit vector times displacement vector. So we have a dot product of unit vector R and ds vector. R unit vector times ds vector, that will be R times ds times cosinus theta, angle theta, between these two vectors. So that will be nothing else as projection of displacement vector on the direction defined by unit vector R. So this will be dr. And this is change of the position vector R. So means that any displacement between points A and B will result in some change of position vector dr at any for any displacement which happens within this range. Taking into account that unit vector is equal to unity, so this is unity, we can write that product, scalar product of unit vector R times displacement vector will be equal just to ds. This is magnitude of displacement vector times cosinus theta. So that can be substituted here instead of this scalar product, like dot product of two vectors. And also we can substitute already this ds times cosinus theta with dr, change of the position vector. We see that if we multiply ds vector on this figure by cosinus theta, that will give us the projection of this ds vector on the direction derived by r unit vector. So that is dr, or in other words, change of position vector. So our expression for the dot product of electric field and position vectors, taking all this consideration into account, will be given as electric constant Ke times Q divided by R square, and instead of scalar product of R unit vector times ds vector, we can now put just dr. So that will be dr. Now we can do some integration already and define how potential difference will be dependent on distance r from our point charge q. Let us do it. We can write that VB minus VA is equal to minus, we can take out from the integral Ke times Q, because this is constant and electric charge is also constant, it doesn't change. So it doesn't depend on position. So Ke times Q integral from position of point A to position of point B. So that is defined by RA and RB. And here we will have dr over r squared. So if we integrate this, we will get rid of this sign minus. So it will be Ke times Q divided by R from RA to RB. Now, if we substitute, we get the final expression that will be Ke times Q 1 over RB minus 1 over RA. So here it is necessary to underline that we determine the difference of potential between point A, B and A. If we want to determine some absolute value of potential in any given point at distance r from our electric charge, we need to arbitrarily define some conditions for zero potential. Usually, kind of intuitively, we can say the following. So let me go to another slide. If distance from electric charge to this point where we define electrostatic potential like approaches infinity, so it's like very far from electric charge, then electric potential at this point will be equal to 0. So that we can choose arbitrary anything, but this kind of makes sense physically reasonable choice. So we consider that at very far distance from electric charge, electric potential is equal to 0. So if we take this into account, and let me write down here this equation for potential difference. So it will be VB minus VA equals to this. So it will be VB minus VA is equal to KE times Q. Here is 1 over RB minus 1 over RA. If we assume that initial point A was located at infinitely far from this electric charge, means RA approaches infinity, then we can neglect with this 1 over RA that will approach to 0. And we will get expression for the absolute value of electrostatic potential at any distance with respect to the electric charge. So V electrostatic potential, we can maybe define it as a function of R, will be equal to KE times Q divided by R. So if we have negative electric charge, then potential will be also negative. So that is a simple equation which provides us information about electrostatic potential distribution around a point charge. So in other words, electrostatic potential is a function of distance from point charge in space, assuming that electrostatic potential at infinitely large distance from this charge is equal to 0. What is important here that we need to focus on the symmetry, like spherical symmetry of this electrostatic potential distribution around point electric charge. We see that at the same at the same distance from electrostatic charge, doesn't matter in which direction. It's just radius, distance of between the point which we pick up to the electric charge. We have the same electrostatic potential. So that means, if we come back to our image here, that so-called equipotential surfaces, they are spheres around with this electric charge in the center. So from this equation which we derive, it is clear that at any distance, like equal distance from, at the same distance from electric charge at any direction, electrostatic potential will be equal. We can, if we want to go from one potential to another, then there will be another equipotential surface. Sorry. Excuse me. So there will be another sphere around this point charge, which will possess also equal potential at each point of this sphere. So we just take with you message that equipotential surfaces in the case of a point charge are spheres with this charge in the center. So now we know how to calculate the electrostatic potential of a point charge at any distance from this point charge. However, this is only for the case when we have a single electric charge. What if we have a system of point electric charges and we want to know also electrostatic potential distribution in the space around this system? So in that case, we have a very simple approach of superposition of these potentials created by each of the electric charges in the system. So we can write that resultant electrostatic potential for such system will be equal to Ke times sum over all charges Qi divided by Ri. So we need to know each magnitude of each charges in the system. Also, we need to know distance from some given point where we want to calculate electrostatic potential to each of electric charges. And then by simple algebraic sum, we get the resultant electrostatic potential. Here it is necessary to underline that this procedure is much easier than determining the electric field vector created by a system of point charges. Any ideas why? Can you explain me why calculating electrostatic potential is easier?
Maybe, can I answer?
Yeah, sure, you're welcome.
I think this is because potential is not vector.
Yeah, exactly. It is scalar, and
Yes.
that's I highlighted this fact that algebraic sum of electrostatic potential. If we deal with the electric field, as you mentioned correctly, it is a vector quantity. So we need to realize not algebraic, but vector sum of each electric field vector created by each of these charges. And that is definitely more challenging procedure than just adding, taking the algebraic sum of electrostatic potential. Good. So now we also need to show how we can calculate potential energy in the system point electric charge and some test charge. So let us assume that we have some positive point electric charge Q, and in this point P, which is at a distance R naught from the point charge Q, from infinity, we move some test charge, positive test charge Q to this point P. So we locate this charge here in this point. We also assume that at infinity, we keep this earlier accepted statement that electrostatic potential at infinity from point charge will be equal to 0. So we move from some point with 0 electrostatic potential, this test charge, to point P at distance R naught from our point charge Q. What will be, since these are two positive charges, they will repel, means that potential energy of such system, point charge Q and test charge Q naught, will be positive. It will be larger than 0. So how we can calculate it? Potential energy will be equal to Q naught times electrostatic potential in this point P. Let's put it VP. Why? Because we consider that initial position was at potential equal to 0, so we just don't consider it. So total potential energy will be Q naught times VP. And that will be equal, if we substitute expression for electrostatic potential next to a point charge, will be Q, first we need our constant, K E Q times Q naught divided by R naught. So that will be potential energy of this system, point charge Q and test charge Q naught. So now we can proceed to our next important topic of today's discussion. That is the relationship of, or in other words, obtaining the value of electric field from electric potential distribution. So we have shown already how we can determine change of electrostatic potential if we know electric field and displacement vector. So some small change of electrostatic potential will be equal to minus electric field vector scalar dot of displacement vector. Now, in order to make it more clear, let us consider only one-dimensional case when we have electric field orientation only along axis x. So in this case, E vector times ds vector will be equal to Ex times dx, because displacement can happen only along axis x, and electric field is also this Ex is aligned along this axis. So they are parallel to each other, and that's why we get just product of their magnitudes. So in this case, taking this into account, if we want to determine small change of electrostatic potential along this axis x, we will get the following: dV, small change of this potential, will be minus Ex times dx. So from here, we can express Ex, electric field. That will be minus dV over dx. So that is very important equation. Need to remember that. How we describe it, that electric field component along axis x is equal to the negative derivative of the electric potential with respect to x position along this axis. Like negative first derivative of potential over x. So it kind of shows us, if we know potential distribution, so the way how fast potential distribution is changes, how fast potential is changing along some unit distance at axis x will define the x component of electric field vector. Obviously, if we have three-dimensional case, then this will be valid for other axes. It will be valid for axis y and z. So we can write that E y component of electric field vector will be equal to dv over dy, and the same for Ez equal minus dv over dz. So what if we are moving along some equipotential surface? So we want to we move from point A to point B, and both of them are located at equipotential surface. In that case, dv is equal to minus E vector times ds vector, and that is equal to 0 because there will be no change in potential if we don't move away from equipotential surface. In order to achieve this, we need to be sure that electric field vector is always perpendicular to displacement vector, ds. And that's why equipotential surfaces should be always perpendicular to electric field. So coming back to our example with point charge, some positive point charge, we know that electric field vector is radially like going out. We can tell also about electric field lines, so that would be probably more descriptive. So they gradually go out from point positive charge, and we know that at any point of this electric field line, tangential will be electric field vector, means that they will just coincide in direction for point charge. So we know that at each, from this statement, we know that equipotential surface should be always perpendicular to electric field vector. And there is no other option as to have this spherical equipotential surfaces with the electric charge, a point electric charge in the center. So which we showed previously in the by deriving the expression for electrostatic potential distribution. And here we also can show it from this condition that the point product of two vectors, electric field and displacement vector, should be equal to 0. So with this, we can also take advantage of spherical symmetry. And if we consider in this spherical symmetry, this product E vector times ds vector, that will be ER times dr. That will be electric field vector magnitude times change of the position vector r. So they will be parallel because it happens along this radial line which goes from the center where electric charge is located to all directions. So if we take this into account, we remember equation for the electric potential distribution around a point charge. That will be Ke times Q divided by R. And now, so we know how electric charge, electric potential is changing around this point charge. We want to determine electric field. And electric field, ER, is equal to minus dV over dr. So it's actually the same, but taking into account the spherical symmetry of electric field around point charge. So now what we need to do, we need to take first derivative of this expression for electrostatic potential around point charge over dr. So that will be equal, here we have minus. If we take derivative here, we will get one more minus, so minus 1 Ke times Q divided by R squared. So we cancel out these two minuses, and eventually we get expression Ke times Q R squared. And that is expression which we derived long time ago for electric field distribution around point charge as a function of distance from given point to electric charge. So indeed, this relationship between electric field and electrostatic potential works. So how it works, how we show this? First, we derived equation which describes electrostatic potential distribution around point charge. Then we apply this relationship between electric field and potential distribution, means that electric field is equal to the derivative of potential over dx, dy, or dz in three-dimensional case. But in our case, when we have spherical symmetry, we can take derivative over dr, just change of position vector. And doing this simple derivation, we like taking this simple derivative, we can show that indeed, eventually we get equation which describes electric field distribution next to a point charge. So this is quite simple, but very clear and straightforward example that indeed this relationship exists, and we can take an advantage of knowing electrostatic potential distribution in order to calculate electric field. Later we will have some examples for doing this, but like which are more complicated. But this is the most simple but straightforward proof of this relationship and this possibility. So now let us try to do some example with calculating electrostatic potential next to two charges. Since we have some minutes left, and let's assume we have X and Y. Here we have some positive charge Q. Here we have some negative charge Q. there is some distance from the origin. It's equal distance A. So we will be interested in determining electric potential at points P at some distance y from the origin and at some point r at distance x from the origin. So let's start first with this point P. So Vp we need to find. So according to this previously introduced equation, since we have a system of two charges, will be QE sum over all charges, QI divided by RI. So then it will be equal to KE and here we have Q divided by distance from first charge, let's say this positive charge, to point P, and that will be given as square root of A square plus Y square. Then we have contribution from the negative charge, minus Q divided by square root, the same. It will be A square plus Y square. If we assume that Q negative absolute value is equal to Q positive absolute value, so these charges are in magnitude the same but different only in sign, then these two terms of this equation, they cancel each other. So we get 0. So there will be 0 potential. Now, maybe let us do it on this part. I can maybe clean this so we can see the image. Now let us try to determine potential at this point R. The same procedure, we need to get a sum of electrostatic potentials created by both charges. VR is equal to KE sum for all charges, QI divided by RI. That will be equal to KE. What is the distance from first positive charge to point R? It will be position of this point R, X plus A. So this will be Q divided by X plus A. Then we have contribution from negative charge. It will be minus Q divided. So distance is this one. And that is X minus A. X minus A. So we can take out from this parenthesis Q, since it is the same for both cases. So KE times Q, and here will be 1 over X plus A minus 1 over X minus A. So if we set to common denominator, we will get the following: KE times Q here is x minus a minus x plus a. Here will be x plus a times x minus a. So that is equal. We can maybe write here. It will be k e times q. So in the numerator, x will be cancelled. So it will be minus 2a minus 2a divided by, and this is just x square minus a square. X square minus a square. So this is the way how we calculate electrostatic potential at points located to the system of point electric charge. In this case, just 2 electric charges. So we have shown how this can be done. With this, I would like to summarize. So we discussed in details and derived equation of electrostatic potential distribution around point electric charge. We have shown that there is a relationship, so that we can use the relationship between electric field and electrostatic potential in order to determine, like calculate electric field distribution from electric potential distribution. And if we consider some direction x, for instance, that will be electric field component along axis x will be equal to negative first derivative of electrostatic potential over dx. That is also valid for all other directions if we have three-dimensional case y and z. And also we did this example of calculating electrostatic potential for the system of 2-point charges when it is necessary to perform algebraic sum of electrostatic potentials in given point created by each of point electric charges. We will continue our discussion on Friday when we already deal with continuum electric charges. And as a result, electrostatic potential and fields created by continuum of electric charges. So if you have any questions, you are welcome. Yeah, if not, then hope you're doing well. Take care and have a good day. See you on Friday.
Thank you. Goodbye.
Thank you. Goodbye.
Bye-bye.
Thank you. Goodbye.